Hello and welcome to Chapter 14 on Oscillations, Part 2. In this second and last part of the lecture, we're going to look at the mass spring system, the pendulum, and the phenomenon called resonance. Let's start by talking about the mass spring oscillator in a little more detail. We introduced this system in part 1 of this lecture. And just to review, the mass spring system has a mass here, this block, and it's attached to a spring where one end of the spring is fixed, for example, against the wall. And typically this system is assumed to be frictionless so that it slides back and forth here without any friction. And due to conservation of energy, this system actually just keeps vibrating or oscillating back and forth as long as there's no friction or air resistance. So we're going to look at the energy of this system and also come up with a formula to figure out the frequency of how fast this thing oscillates back and forth. So energy in the mass spring system is related to some concepts that we learned earlier in the course. So there's really nothing new here. In particular, there are two types of energy that the mass spring system has. That is the potential energy due to the elastic potential energy in the spring. And remember in chapter 10, we learned that elastic potential energy, U, is equal to 1/2 kx squared, where K is the spring constant. That is a measure of how stiff the spring is. And X here is the displacement of the spring, meaning how far is the spring either compressed or stretched. The other type of energy that the system has is the kinetic energy due to the motion of the block. And kinetic energy, again, from chapter 10, was found to be 1/2 mv squared, where m is the mass of the block at the end of the spring, and v is the speed that the block moves. So the total energy of the mass spring system, E total, is just the sum of the kinetic energy plus the potential energy, K plus U. And because of conservation of energy, that total energy is constant. It doesn't change. It will go back and forth between kinetic and potential energy as this thing slides back and forth. However, the total amount of energy has to remain the same because energy can't be created or destroyed. So the total energy of the system is the kinetic energy, 1/2 mv squared, plus the elastic potential energy, 1/2 kx squared. And again, that's equal to a constant. Now, there's a more convenient equation to figure out the total energy of a mass spring system. And this uses a little trick. If we think about this mass on the spring vibrating back and forth, all right, this is the equilibrium position here. So this is where it would be at rest if it were not moving. If it moves over here to the right, this is the amplitude. Okay, so if you look down here, you can see the x-axis. So 0 is our equilibrium position. Over here is A, which is for the amplitude. So this is the maximum distance the object swings over to the right, and then of course it's going to swing back past equilibrium and is going to end up over here at minus A, which is again the distance, the same distance from equilibrium as this distance over here, but it's on the left side. So you can see down here it's at minus A. The key thing is this mass oscillates back and forth between minus A and positive A, and back and forth. This position right here and this position here are called turnaround points. These are the endpoints where the mass has to stop moving and change direction. So it's going to come over here, briefly stop, and then start moving back this way, stop here, and then start moving back the other way. So when it stops at these turnaround points or stopping points, there is no kinetic energy. So this term here, 1/2 mv squared, is 0. So all of the energy is elastic potential energy, and the x value at this point right here, remember we can read it off right down here, is equal to A, the amplitude of oscillation. So the total energy of the mass spring system is equal to the maximum potential energy, which is just 1/2 K A squared. So if we know the spring constant and we know the amplitude of oscillation, A, we know the total energy of the oscillator. Another way to think of this is when the mass moves through the center, right when it gets to the middle part here, remember this is when x is equal to 0, the spring has no potential energy because this is the equilibrium position of the spring when it's relaxed. So the spring is not storing any potential energy here. So where is all the energy gone? Well, it's all kinetic energy. So that means the mass is moving the fastest when it reaches the center point right here at x equals 0. So the other way we can determine the total energy is the maximum kinetic energy, which is 1/2 m V max squared, where V max is the maximum speed that the block obtains. So putting all of this together, we can sort of summarize it all with one long equation here for the total energy of the mass spring system. The total energy, you can think of it three ways. It's 1/2 mv squared plus 1/2 kx squared. It's also equal to 1/2 k a squared. And it's also equal to 1/2 m v max squared. We'll look at an example where we use these equations shortly. The other important thing that we still need to figure out here is to determine the oscillation frequency of the mass spring system. In other words, how fast does this thing oscillate back and forth? We're not going to derive the formula in this course. It's actually not that difficult to do, but it would take several steps. So I'm just going to state the result here, and this is the useful form that we're going to use. The oscillation frequency is given by this equation right here. It's 1/2 pi times the square root of k over m. Now, what is k? Well, k is the spring constant, and m is the mass of this block that's on the end of the spring. So what this tells us are a couple things. First of all, stiffer springs produce higher frequencies. Notice that k is up here in the numerator. So if k is larger, meaning a stiffer spring, that means F will be larger. That means it'll have a higher frequency. And this, of course, makes sense. If the spring is stiffer, if it has a larger spring constant, K, then it's going to accelerate this mass faster, more quickly, because a stiffer spring has more force. So it's going to shake this mass back and forth more quickly, higher frequency. On the other hand, notice the mass is down here in the denominator, so a smaller mass will make for a larger frequency. All right, so lighter, number 2 here, a lighter mass produces a higher frequency. This also makes sense. From Newton's second law, F equals ma. So we know that the acceleration of an object is equal to force divided by its mass. So a lighter mass, a smaller mass, is easier to accelerate. That means it's going to be able to wiggle back and forth at a higher frequency. So those are the two things that determine the frequency of the mass spring system. And interestingly, it's only the spring constant and the mass of the object. Notice there's no amplitude in this equation. So the frequency of oscillation is independent of the amplitude, meaning whether this thing is wiggling just a little bit or whether it's wiggling a far distance like this, it will always have the same frequency. Let's go ahead and watch a demonstration using a simulation tool to illustrate these three characteristics of the mass spring system. This is the spring pendulum simulation tool that we saw earlier in this chapter's lecture. And I'm going to use it again to show several of the important properties of oscillation systems, in particular when we have a mass on a spring like this. So the first thing I'm going to do is just a review. We actually saw this earlier. I'm going to show you that the frequency of oscillation is independent of the amplitude. And the way I'm going to do that is I'm going to get these two pendulums oscillating with different amplitudes. Let me get it started here. So I've released the one on the right at the same time as the one on the left. And let's go to normal speed so we can watch these. So what we're seeing here now is that this one on the left is moving just a little bit. It has a small amplitude. And the one on the right is moving a large distance, meaning it has a large amplitude. However, you'll notice that both pendulums have exactly the same period and the same frequency. Notice they're both going up at the same time and both going down at the same time. This one over here on the right is just moving faster and it's going farther. But they both reach the top and they both reach the bottom at precisely the same time. So both pendulums here have the same period and same frequency, and it's completely independent of the amplitude. Let's do something else now. I'm going to go ahead and stop these two pendulums. The next thing we're going to investigate is the effect of the spring constant on the pendulum. So again, let's get this one over here on the left moving. I'm going to pull it down like this and let it get started. And on the one on the right, what I'm going to do is up here you can see this little slider. I can adjust the spring and make it stiffer. All right, so let me go ahead and stop it first. So you can see the spring here, how thick the coils are now compared to the real thin wires over here. So this spring is a lot stiffer. It has a higher spring constant, K. So let's get this one oscillating and watch the difference in frequency now. So now you can see there's a big difference in frequency. The stiffer spring is pulling harder, and therefore it's going to accelerate the mass more quickly, and it can move back and forth a lot faster. So we see a larger frequency of oscillation with a stiffer spring with the value of K, and we saw that in the equation for the frequency. And I can, I can move my slider, and I can make it back to a small spring constant like this, and now they're actually going to be back in sync, especially if I start it at the right time, something like this. You can see they're basically moving together again. All right, the next thing we can do here is investigate the effect of the mass of the object on the frequency. So I'm going to change these springs here. Let me stop this. I'm going to go to a stiff spring for both of them. And let's take off this 100 gram mass and let's put on a big 250 gram mass like this. All right, and so what we're going to do now is, again, we're going to start these two oscillators. Let's start the heavy mass over here and we'll get it going. And now we'll start the lighter mass here and get it going. So notice there's a huge difference again in the frequency of oscillation. Now remember, both springs are identical. They're both set to the highest value of spring constant. So they're very stiff, strong springs. The difference now, of course, is the mass. And notice that the larger mass on the right moves slower. And this is not a surprise because remember, it's harder to move a larger mass. It has more inertia. And by Newton's second law, F equals ma, we note that the heavier, more massive objects have less acceleration. So this, on the other, in contrast, the lighter mass on the left is much easier to accelerate. So the spring is able to move it back and forth very quickly. Therefore, it has a larger frequency of oscillation. This slide is just a summary of the formulas that we've just introduced for the mass spring system. Remember that the idea here with a mass spring system is we have a mass on the end of a spring, and this mass is going to oscillate back and forth. The central position here is, we'll call that our origin. That's when x is equal to 0, meaning the spring has not been stretched or compressed. This is the relaxed position of the spring. The maximum distance that it moves to the right is called the amplitude, which is A, and the maximum distance that it moves to the left will be at negative A. Notice the oscillations are symmetric about the origin here. So I won't go through all of these equations again because we've just introduced them all in the last couple of slides, but these are the equations for potential energy. Here are equations for kinetic energy. These are the equations for total energy. And then down here is the equation we just learned for the frequency of the mass spring oscillator. And remember that frequency and period are reciprocals of each other. So if you take the reciprocal of the frequency, F, you get the period T. So, and the period is then 2 pi times the square root of m over k, which is just, you know, the reciprocal of this result over here. Let's go ahead and work through an example that pretty much shows all of the equations and characteristics that we've learned about the mass spring system. So this is an important example to know in order to do the homework and also to do well on the quiz for this chapter. So in this example, we have a 5 kilogram mass, that's this guy out here, is connected to a spring and sits at position x equals 0 at rest. The mass is pulled to the position x equals 0.5 meters, which is over here, and then it's released. Actually, it tells us also that when it's over here at 0.5 meters, the force from the spring is 20 newtons. The mass is then released. So once we release the mass from over here, it's going to start to oscillate, and it's going to go back and forth like this. So we have a whole bunch of questions here, 9 total questions that will illustrate many of the properties of the mass spring oscillator. So the first one is sort of a review question for us. What is the spring constant? Well, remember, the spring constant is given from Hooke's law, F equals kx. So the spring constant K is the force, F, divided by x, the displacement. So we were told that the force is 20 newtons when the displacement was 0.5 meters. So 20 divided by 0.5 is 40 newtons per meter. So that's our spring constant. Question number 2. Find the system's total energy. So here we're going to use the total energy equation 1/2 Ka squared. So we now know K is 40, and we know the amplitude is over here. That's 0.5 meters. And we have to square that, so we do that 0.5 squared times 40 times 1/2 gives us a total system energy of 5 joules. Question number 3 says, as the mass oscillates back and forth, where are the turning points? Well, this is simple. The mass, remember, we started over here at 0.5. It's going to oscillate back the same amount in the left direction, which would be at negative 0.5. So our 2 turning points are negative 0.5 meters and positive 0.5 meters. Question number 4 asks, where is the energy all potential energy? Well, remember, potential energy is max when there is no kinetic energy. That means this object is not moving. The 2 places where it comes to rest are at negative 0.5 and positive 0.5. These are the 2 turning points. Question number 5, what is the potential energy at the turning points? Well, at these turning points, we have maximum potential energy. So the energy there is given by 1/2 Ka squared, which is exactly what we did up here. And that, again, is 5 joules. Question number 6, where is the energy all kinetic energy? And how much kinetic energy is there at that position? Well, remember that when we have all kinetic energy, that means there's no potential energy. So that means the spring must be relaxed at that point. And that happens here at the origin when x is equal to 0. And the energy here, we know, must be the same as the energy here and the energy here because of conservation of energy. All right, and so the total energy of the system is 5 joules, so that is our maximum kinetic energy as well. Number 7 asks, what is V max? In other words, what is the maximum speed of this object? Well, it's going to happen right here at when x is equal to 0. What we can do here is we can say that 1/2 mv max squared, which is the total kinetic energy, maximum kinetic energy, I'm sorry, is equal to the maximum potential energy because of conservation of energy. All right, here we have all kinetic. Over here we have all potential, but they have to be equal to each other. So 1/2 mv max squared is equal to 1/2 ka squared, and now we can solve for v max. So we can get rid of the 1/2s, we can cancel those out, and after we solve for v max, we get a times the square root of k over m, and we can plug in our numbers. A is 0.5, k is 40, and the mass is 5. And this comes out to be 1.41 meters per second. Question number 8, what is the oscillation frequency in period? So here we're going to use our equation for frequency. Frequency is 1/2 pi times the square root of k over m. So k is 40 and m is 5 kilograms. So 40 divided by 5 is 8. Take the square root of 8 and basically divide it by 2 pi, and you'll get 0.45 hertz. The period t is just 1 over the frequency. Remember, these have a reciprocal relationship. So 1 over 0.45 gives us 2.22 seconds. This is how long it takes for the mass to go from here all the way to the left and all the way back to where it started from. That's the period there. Finally, question number 9, what is the velocity at x equals 0.2 meters? So we're asking, what is the velocity somewhere around here? So here we're going to use, remember we have E total, which is 1/2 ka squared, is equal to, this is another expression for the total energy, 1/2 mv squared, that's the kinetic energy, plus 1/2 kx squared, which is the elastic potential energy. So what we need to do is basically solve this equation here for x. So the first thing we can do is get rid of all these 1/2s, so we can cancel those out. They're on each term. So we get ka squared equals mv squared plus kx squared. Let's see, we're trying to figure out, actually we're solving for velocity, v. So let's put this mv squared term by itself. So mv squared equals ka squared minus kx squared. And now we can take this, we can divide by m, all right, to get rid of the m over here. And then we can take the square root of the whole thing. So we end up with this equation here. V is equal to the square root of k times quantity a squared minus x squared, all over m, and then remember that whole thing is square rooted. So after we plug in the values for k, a, and remember x is 0.2, mass is 5, we get 1.3 meters per second. So now we're going to turn to another very important simple oscillator system, and this is the pendulum. The pendulum has a mass down here which hangs from a string or a rope or a cable, and it swings back and forth like this. The pendulum mass down here is often called the bob. So this is the bob of the pendulum, which is swinging back and forth due to gravity. So this chart here, or slide, has several formulas for pendulum energy and frequency. I'm not going to go through the details of deriving all these formulas. Instead, we're just going to use the results to figure out some of the characteristics of the pendulum. Basically, though, again, the main idea is that the pendulum, the total energy of a pendulum, is due to two things. It has kinetic energy, K, which is 1/2 mv squared, and it has potential energy, not due to a spring, but due to gravity, because the pendulum swings up in the air. So this U term here is gravitational potential energy, which remember is mgh. So after doing some geometry with the pendulum and so forth, we get this formula here that the total energy of the pendulum is equal to this, mg times a, which is the amplitude squared, divided by 2 times L. L is the length of the string here. So the total energy is also equal to 1/2 mv max squared. And V max can be determined using two formulas shown here. Again, I'm not going to prove these in this lecture, but one of them is the amplitude times the square root of G, which is 9.8, divided by the length of the string, or Vmax, the maximum speed of the pendulum, is found by 2 pi times the frequency times the amplitude. And then by combining some of these equations up here, we come to probably the most important formula for the pendulum, and this is the pendulum frequency. It's given by 1 over 2 pi times the square root of G over L. So this is kind of interesting here. Notice the only parameter that the frequency depends on is the length of the string. All right. Now remember, G, that on Earth, G is always 9.8. Obviously, if you take a pendulum to the moon, it's going to behave differently because it'll have a different G. But here on Earth, the only thing that affects the frequency of the pendulum is the length of the string. Notice that the mass, M, which we see in these equations up here, the mass disappears. It cancels out. There's no m in this equation. So the frequency of the pendulum is independent of mass and also the amplitude. Remember, here's the A here, here's an A here, and here's an A. The A's cancel out as well. There's no amplitude in here. So the pendulum only depends on the length of the string, not on the mass or the amplitude. This will become very clear when you watch the demo coming up now. Here we see the pendulum simulation tool again that we saw earlier in this chapter, and I'm going to use it again to show you several important properties of pendulums. The first one we actually saw before, but I'm going to review it now, and that is the frequency of the pendulum is independent of the amplitude. In other words, how fast or the frequency, how many cycles per second of the pendulum, it does not depend on how far the pendulum swings. So to show this, let's take, I've got two pendulums here, one on top of the other. Let's take the red one and I'm going to move it over 5 degrees and get it swinging. And I'll take the blue one and I'm going to move it over here 10 degrees. And as soon as the other one reaches its peak, I will let them go. So they're both swinging together now. Now I'm going to go back to normal speed and let's watch them swing. So we saw this demonstration earlier. Notice that even though the blue pendulum is swinging twice as far, it has twice the amplitude, but its frequency is exactly the same as the red pendulum. Okay, and this is one reason that pendulums were used to make clocks. For example, the old grandfather's clock that you may have seen, they keep very good time because the amplitude does not affect how long it takes for the pendulum bob to swing back and forth. Okay, so that's our first property there. Let's look at something else. We can change the mass of the pendulum by going up here and let's make mass 2, we'll make it larger like this. All right, so what I'm going to do now is I'm going to swing this again at 10 degrees and let's get it going. And I'll grab the blue one and I'll swing it at 10 degrees. Actually, let me redo this. I'm going to start it in slow motion. It's a lot easier to get them to start at the same time. Like this. Here we go. So I'm going to release it right now. And you can see the, actually, let me do this so you can see them better. I'll switch the masses. There we go. So now I've got the blue mass is set to 1.5 kilograms up here, and the red mass is a smaller one. It's set to 0.1. So it's 15 times lighter. But notice that they're both swinging exactly together. In fact, let me go to normal speed here, and you can see that in a little more detail there. So they both have the same frequency and period again. So this is another interesting thing about the pendulum on a string, is that the frequency and the period, it's independent not just of the amplitude, but it's also independent of the mass of the object. So surprisingly, the heavier mass and the lighter mass swing at exactly the same rate and the same frequency. How can we affect the pendulum's frequency? Well, the only thing that really matters is the length of the string. And so to show this, let me move both of these masses together like this, and I'm going to take the red pendulum and I'm going to shorten its string, something like this. All right, and now notice, the long string here has a relatively small frequency, a very low frequency. It takes a long time to go back and forth, but look at how quickly the red pendulum up here is swinging back and forth. So we saw this in the equation that the pendulum's frequency is inversely proportional to the length of the string. So the shorter string produces a higher frequency of oscillation. An important cousin of the pendulum is called the physical pendulum. And a physical pendulum consists of a swinging rigid body. So instead of having all of the mass down at the bottom, connected to a string, a physical pendulum, you can think of a solid object like this. There's a pivot up here where it's attached, and this whole object is swinging back and forth. So if you take a piece of wood and pound a nail through it like this, this piece of wood can swing back and forth with the nail as a pivot. One of the important biomechanical examples of physical pendulums are limbs. Walking is basically, you can kind of think of walking as having your leg swinging on the pivot point, which would be the hip joint, and also when you walk, your arms swing back and forth. So your legs and your arms act as physical pendulums, and our natural walking speed matches basically the frequency of the physical pendulum, because this makes it easier to walk when we walk so that our arms and legs are swinging at their natural speeds. And this is a formula up here for the frequency of the physical pendulum. It's a little bit different than the regular pendulum. It has a couple of things in here. First of all, it has I down here, which is the rotational inertia of the pendulum. And also it has D, which is sort of like the length. That's the pivot to, this is the distance from the pivot point, up here, say, to not down to the bottom, all right, but it's to the center of gravity. The last topic of this chapter is on driven oscillations and resonance. So what do we mean by driven oscillations? Well, a driven oscillation is basically an oscillation that is forced from some outside force that's making the oscillation or the system move back and forth. So there are two frequencies that are important to keep in mind here. There is the driving frequency, which we'll call F external. That's the frequency of an external periodic force that drives a system by wiggling it, basically, okay? But the system has its own natural frequency, F naught, or F sub 0. This is the oscillation frequency of the system if it is left by itself with no driving frequency present. So up until now, we have been dealing with systems and only talking about the natural frequency of the system. For example, when we talked about the mass spring system, we had a formula for frequency. That's the natural frequency of the mass spring system. When we talked about the pendulum, we talked about the natural frequency of the pendulum. But now we're going to add something else. We're going to allow an external force to come along and make the system oscillate at a different frequency. So this is what's meant by a driven oscillation. So to make this very clear, here's some examples that are pretty common. When you push someone on a swing like this, okay, the person here is the driving force that's going to be pushing the child at some frequency, okay? And we'll talk about resonance soon. When a diver here jumps up and down on the springboard here, all right, that's the driving frequency. An earthquake will has its own frequency as it shakes through the ground. And when an earthquake shakes a building, for example, the earthquake is producing the driving frequency up here. When you drive your car over a bumpy road, the bumps in the road are causing your car to shake or vibrate. And that is a vibrating frequency caused by the road and, of course, the speed that you're driving by. Sound waves that hit your eardrum. When you listen to music, different sound waves have different frequencies. And those different sound wave frequencies are making your eardrum vibrate at that particular frequency. Okay, so let's now take a look at the response curve of a system to different driving frequencies. So when you drive a system by wiggling it at some frequency, the system will oscillate at the driving frequency. However, the amplitude of the driven oscillations depends on the frequency. So take a look at this graph here. This is showing the amplitude, meaning how much the system actually oscillates, right? The distance that it oscillates. And we're going to plot this versus the driving frequency, F external, down here in hertz. All right. Now, the system has a natural frequency of 2 hertz in this example. All right. So F naught is 2 hertz. This would be the frequency of the system if it was just by itself and bouncing back and forth. But now what we're going to do is we're going to drive the system externally by pushing the system at 1 hertz. And you can see that the amplitude is very small. But look what happens as we approach the natural frequency of the system. As we get to 2 hertz, we reach a peak. And this is called resonance. All right, our driving frequency is resonating with the system here at the correct system frequency, which produces the maximum response of the system. We get the highest amplitude right here when we match our driving frequency to the system's natural frequency. Once we go past that frequency, though, you can see the amplitude of oscillations starts to die back down. So this phenomenon that we just saw on the last slide is called resonance. Resonance is the condition when a vibration's amplitude grows very large due to an external influence that has the same frequency as the vibration. So one example that makes this very clear is to think about how do you push a child on the swing? So the swing has a natural frequency that it wants to swing back and forth. And you can see here that the swing is just a pendulum, right? Here's the mass of the pendulum here, which is the child, and the rope or the cable or the chain that the swing is attached to, that this is the length of the pendulum. So remember the pendulum has a frequency which is determined by this length here. So this swing wants to swing back and forth at a certain frequency. So how does the mom here push the child to make it swing faster and higher? Well, she pushes at the exact same frequency as the swing. In other words, every time the swing comes over here, she gives the child a little push back in the other direction. And if she keeps doing this, the child starts to swing higher and higher and higher because there is resonance involved here, right? The mother's frequency is matching the natural frequency of the swing, and this is called resonance. If the mom here pushes at any other frequency, if she pushes too often or not often enough, the child's amplitude here will diminish and the child will end up just not swinging at all. So let's look at a resonance simulation tool, and we can look at this with a little bit different system. This is a simulation tool that is useful to simulate the phenomena of resonance. And the way it works here is they've got this system down here called a driver. And the driver has a piston here that's going to move up and down, and we can set the frequency at which it moves up and down. And then you can see there's a spring attached to that, and on top of the spring is a mass, this blue block. So what I'm going to do here is start this thing oscillating just really slowly at first. We'll set it to about 0.2 hertz. Let's get this thing going here. Here it goes. Okay, so you can see this thing going down at, up and down at 0.2 hertz. So it's taking about 5 seconds to go up and down once. And you can see that the mass up here is moving up and down with the driver here. Okay, now notice over here the resonator, that's the spring and the mass. It has a calculator in there that calculates the natural frequency, and the natural frequency is set so that it's 1 hertz, 1 cycle per second. But notice we're not matching that. We're only at 0.2 hertz or 0.2 cycles per second. So as a result, we don't have any resonance right here. Now let's watch what happens as I start to increase our frequency here. Let's go up to this is about 0.5, and you can see now this thing is still, it's moving basically with the driver here, but watch what happens as we start going closer and closer to 1. Now we're starting to see the mass up here is actually moving with more amplitude than the driver is here. And as we get closer and closer to the natural frequency, we reach resonance. So look what happens as I get to 1 hertz down here. We've got, this is resonance now. So notice the mass is just going crazy right now, right? The amplitude is increasing every time it pushes it. It increases it more and more. Now as I go past 1 hertz, all right, now I'm not matched to the resonant frequency anymore. You'll see the amplitude of oscillation starts to decrease. And that continues as I go up. I can go, I'm at 2 hertz now. You can see how fast this thing is moving. But notice this, this mass up here has very little response to it. All right, and I can keep going up in frequency. Here I'm going really fast, and notice the mass is basically almost not moving at all. So the key idea, remember, with resonance is we want the driving frequency, the pushing frequency, to match the natural frequency of this spring and mass, and it's set to 1 hertz. So I have to slow this thing back down, and let's go back down. I'll crank this thing back down till we get to 1 hertz, and now watch the amplitude start to increase as I get to 1 hertz. Right about here, we're at resonance again. And so now the mass really has a large amplitude. And then of course if I decrease the frequency, we're not at resonance anymore, and now you're going to see the amplitude starts to decrease. Resonance is a fascinating phenomenon in physics, and there are lots of examples of resonance. Some of you have maybe experienced this. It's kind of fun if you take a wine glass and you dip your finger in water and rub the top of the glass, you can get the wine glass to actually sing. And what's happening there is the vibrations of your finger rubbing on the rim of the glass, they get to resonance with the glass natural frequency. And when this happens, the amplitude of vibrations builds up until the glass actually vibrates so much that it produces sound. But you have to use the right amount of pressure with your finger and the right speed of your finger to produce the right frequency, that is the right driving frequency, to match the wine glass's natural frequency. And you can take this to an extreme by actually getting a wine glass to shatter from just sound. And you'll watch a kind of a very entertaining and fun video of this shortly. Sometimes you may have heard windows in your house rattle when you're listening to loud music, or maybe the TV is playing some music or something, and sometimes you'll hear something in the house like something on a shelf or maybe a window will all of a sudden rattle. Well, what's happened there is you've reached resonance. The natural frequency of the window is matched by the driving frequency of the sound, and only certain sounds will cause that resonance. The same thing for those annoying vibrations that you sometimes hear in your car. You might have something on your on the dashboard of your car, or maybe your glove compartment door or something will sometimes vibrate when and you'll hear it buzzing when you drive your car at certain speeds. This is because the vibration resonance matches the vibration of the road or the car basically comes to match the natural vibration frequency of the object that is vibrating, and we get resonance there. Many years ago, the military learned that the hard way, basically, that if they had soldiers marching in step over a bridge, and if the frequency of their steps just so happened to match the resonant or natural frequency of the bridge would start to vibrate. And it can actually vibrate to the point where the bridge can break, which would be horrible, right? So what they would typically do is have the soldiers break their lockstep and just walk casually on the bridge so as not to create a resonant situation. You may have noticed this back, on our campus and the pedestrian bridge that goes to the parking structure. Sometimes when you walk across that, you can feel the bridge shaking up and down a little bit, and that is due to resonance of the people on the bridge walking over it. Taking this to an extreme, there's a famous or maybe infamous example of the Tacoma Narrows Bridge disaster, where wind caused vibrations that matched the resonant frequency of the bridge, and the result was catastrophic. So you'll watch a short video clip of that very soon. Lots of other important examples of resonance. For example, the whole idea of musical instruments is based on acoustic resonance, and this is something that we're going to explore in the next couple of chapters. Lasers, if you think of a laser pointer or an industrial laser that cuts metal, the whole idea of a laser is based on optical resonance. A radio, including the radios in your smartphone, your telephone, your cell phone is basically a radio receiver and transmitter, relies on the phenomenon of electrical resonance. So the last thing we're going to do here is watch a couple of fun videos. I think you'll enjoy these. They show some of the very fascinating effects of resonance. And after that, I will see you in chapter 15. Goodbye.
Yes! All right. Yes! Glass number 90. You! And that's proof that it's not a trick. That was too easy, man. Number 93. That's 5 today.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.